Hello students, this is Professor Chalai, and in this video we're going to look at Lewis symbols for atoms and ions. As always, you can follow along with our Chapter 7 workbook. By the end of this video, you should be able to draw the Lewis structures for neutral atoms and for ions. Now, in our last few videos, we've been looking at electron configurations and also bonding, ionic bonding, covalent bonding, and we talked a little bit about how those are related to the electron configurations. The Lewis structure is simply a way to represent those atoms or ions, and more specifically represent them with their valence electrons. So we talked about how the valence electrons are those with the highest n values, right? The principal quantum number n. That means that they're the electrons that are furthest away from the nucleus of the atom, right? So if you can imagine an atom, those will be your n equals 1 electron and so on. Your valence electrons are going to be furthest away from the atom, nucleus of the atom, which means that if anything interesting is going to happen, like they form bonds or react or any of that, they're going to do so with the valence electrons and not with the core electrons. So when we want to draw a structure representing how atoms might bond together, we would want to represent their valence electrons because those are the important electrons. So let's look at an example with an oxygen atom. We've done this a few times before. We know the electron configuration is, because it has 8 electrons, 1 has 2, 2 has 2, and 2p4. So if I were to draw this, the orbital diagram, 1s will be filled with a pair of electrons, 2s with a pair of electrons, and the 2p orbitals, there'll be 1 pair and 2 unpaired electrons in oxygen. What the Lewis structure is for this atom is a way to represent all of the valence electrons, which would be everything in the n equals 2 orbitals. So that'll include the 2s and the 2p orbitals because that's the highest n value. Those are the valence electrons. So we need a way to represent these 1, 2, 3, 4, 5, 6 electrons around oxygen in its valence electrons in oxygen. And the way we're going to do that is by using dots. Every dot around an atom is going to be 1 electron. And we're going to group them depending on how many pairs we have. So we have 2 pairs of electrons. So we're going to have 2 sets of dots that are closely spaced. They're paired. And then we have 2 electrons that are unpaired. So we'll put 1 dot separated out there and one other dot separated there as unpaired. So here we have 1, 2, 3, 4, 5, 6 valence electrons around oxygen, which is exactly how much we needed. And that's it. That's a Lewis structure of an atom. What we need to recognize is what their valence electron orbital diagram looks like, so we know how many paired or unpaired electrons we have, and then we just put dots around the atom to represent those paired and unpaired electrons. So with that, let's do a few of these for practice. Number 4, A, B, and C. Pause the video, see if you can draw the Lewis structures with dots representing the electrons. And when you're done, you can unpause and we'll go over them together. Okay, so let's look at beryllium. We need to start with the electron configuration before we can draw the Lewis structure. And beryllium is right here in the periodic table, which means that we have helium, and then this is the n equals 1 and n equals 2. So helium and then 2s2, right? So for beryllium, we'll have an electron configuration like helium, and then this will be the 2s orbital with 2 electrons in it. So how many valence electrons does beryllium have? Only 2. So if we're going to write the electron configuration, draw the Lewis structure for beryllium, it'll be beryllium with 2 electrons and they're paired, so 2 dots right next to each other. I'm going to use a different color to represent those dots. There we go. 2 dots for the valence electrons that are paired. Let's look at fluorine. Where's fluorine on the periodic table? Well, fluorine is right here. So again, we start with helium as the highest noble gas that's lower than fluorine, and then we'll have the 2s and the 2p orbitals. 2s will be full, and then the 2p will have 1, 2, 3, 4, 5 electrons in them. So let's draw the orbital diagram for that. So we'll start with helium. Then we'll have the 2s that we just said was full. And then the 2p, which will have 5 electrons in them. So let's fill these out. 1, 2, 3, 1, 2, 3, 4, 5. So that's the electron configuration for fluorine with the orbital energy diagram. So to draw the Lewis structure, it will be just an F with 1, 2, 3 pairs of electrons. So 1 pair, 2 pair, 3 pairs of electrons, and then 1 electron that's unpaired. So we'll put that right there without any partners. That's the electron Lewis structure for fluorine. Let's look at phosphorus. Again, we can do this a little bit faster. So phosphorus is here on the periodic table. So we can start with neon, and then this will be 3s2, 3p1, 2, 3. So we'll have neon, 3s2, 3p3. So 1, 2, 3. That's phosphorus. Let's make sure we label this as 3p. And so the phosphorus Lewis structure will be 1 paired and 1, 2, 3 unpaired. So 1 pair and 1, 2, 3 unpaired. That's the Lewis structure for phosphorus. Again, we're only drawing dots for the valence electrons. In this case, the valence electrons were all in the n equals 3 level. Okay, let's move on to ions. Ions are the same thing, except we need to add or remove electrons depending on whether we're forming positive or negative ions. For example, let's look at calcium and chlorine. Calcium, right, it's right here. So in the valence orbital, we'll have 1, 2 paired electrons in the 4s orbital, right? And for, I already forgot what the other one was, chlorine. Chlorine is here, which means in the 3s orbital, we'll have 2 paired up electrons, and then we'll have 1, 2, 3, 4, 5 electrons in the 3p orbitals. So if we were to draw the Lewis structures, this is what they will look like. In case you were wondering, calcium was going to be 3s with 2 electrons in it. That was for calcium. That's where the pair of electrons come from. And for chlorine, we had the 2s with a pair of electrons, and then the 2p with a pair of electrons in these two, and then 1 unpaired there. So that's why we have 1, 2, 3 pairs. So 1, 2, 3 pairs, and 1 unpaired for chlorine. Okay, so those are the electronic structure of calcium, the Lewis structures for calcium and chlorine. However, we know that when calcium forms an ion, it loses 2 electrons, right, to form a 2+ ion. So guess what would happen? These 2 electrons would just disappear. So for calcium, this is the Lewis structure. There are no dots because all of its valence electrons were removed. We learned in a previous video that a lot of metals form ions by losing all of their valence electrons so that they can have a completely empty set of orbitals, which makes it more stable. So here, calcium lost all of its valence electrons, so there's no dots to draw. We just have to make sure that we put the 2+ symbol right there to make sure that we let people know that it has a charge. Chlorine does the opposite, right? It gains 1 electron so that it could complete its valence orbitals, have a completely filled 2p subshell, or 3p subshell actually. Yep, 3p. There we go. I misspoke. Okay, so chlorine will gain 1 electron to complete its orbitals full of electrons. So now it's going to look like this with 4 pairs of electrons. Again, if I were to draw this, we'll have the 3s and the 3p, right? Chlorine started out with like this, and then it's going to add 1 more electron, that 1 more electron to completely fill its orbitals, and that's why it gets a -1 charge. And so we'll draw it with 1, 2, 3, 4 pairs of electrons. So we have 1, 2, 3, 4 pairs of electrons. And we need to add a negative sign there to show that the whole thing has a -1 charge. And we put the whole thing in brackets, in parentheses, just to make it nicer. Okay, so for the ion calcium chloride, right, CaCl2, you can write it as Ca2+, right? That's the Lewis structure for calcium. And then we have 2 of these Cl minuses. And that's calcium chloride Lewis structure. All right, with that, let's practice drawing Lewis structures for all of the different ions in these compounds. Take a minute, pause the video here, and then we'll go over it together. Okay, for NaCl, we know that the ions that we're dealing with are Na plus and Cl minus. We already drew the Lewis structures for Cl minus, right? It's Cl with 1, 2, 3, 4. Again, I just realized I should probably use a different color for the dots. 1, 2, 3, 4, 5, 6, 7, 8, 4 pairs, and the whole thing has a negative charge. So that's for Cl minus. For Na plus, let's look at what it is. Sodium is here in the periodic table, right? Which means for the valence orbitals, this is the 3s orbital, it'll have only 1 electron in it, and it'll not be paired. So sodium will just have 1 electron there, unpaired. That's a Lewis structure. But to form sodium plus, we need to remove 1 electron, and so this is what the sodium plus Lewis structure is. So for sodium chloride, it'll just be sodium plus, no dots because there's no valence electrons. And then right next to that, we'll have Cl minus with 1, 2, 3, 4, 5, 6, 7, 8 electrons. That's a Lewis structure for sodium chloride. Let's look at magnesium oxide. Magnesium is right next to sodium on the periodic table. So it'll have the 3s orbital with 2 electrons in it, right? And nothing else. So it'll only have 1 pair of electrons in there. So magnesium, right, will have 1 pair of electrons in there. But we know that from magnesium oxide, the ions are going to be magnesium 2 plus and oxide ion is O2 minus. So for magnesium 2 plus, we need to remove these 2 electrons, and which makes the whole thing 2 plus. Let's do oxygen. We did oxygen earlier, but we're going to do it again. Here is oxygen. Let's erase some of these things on the periodic table so we can make things clearer. Okay, here is oxygen. The valence electrons for oxygen will be 2 in the 2s orbitals and 1, 2, 3, 4 in the 2p orbitals. So let's draw that just to make it clear. So the 2s orbitals and the 2p orbitals. In the 2s we said we'll have a pair, and in the 2p we'll have 1, 2, 3, 4 electrons. So this tells us that for oxygen we'll have 1, 2 pairs. So 1 pair of electrons, 2 pairs of electrons from these, and then 2 unpaired electrons, 1, 2. So I'll draw 1, 2. For oxygen to form an O2 minus charge, it must gain 2 electrons. So there's 2 spaces there to gain electrons, and so we'll just gain 1, 2 electrons there to completely fill our orbitals. And so if we think about it here, these 2 electrons that were once unpaired now have partners, and so we add 2 electrons there, and so this whole thing, we'll put in square brackets, has a 2 minus charge. So for Mg2 plus and O2 minus, this is the Lewis structure that we have. No valence electrons on the magnesium, 8 valence electrons on the oxygen for oxide. Finally, let's do FeCl2. FeCl2 we know that the chlorides have a charge of 1 minus, which means that if there are 2 of them, this iron has a charge of 2 plus. Let's look at iron, right? Because iron can be tricky. So we know that iron will have electrons in its 4s subshells and its 3d subshells. Now, remember our valence electrons are only in the outermost n value. So technically, the 4s subshell is more outer, even though it's lower in energy, than the 3D subshell. So we can ignore for now the 3D electrons. And so there are going to be 2 electrons in the 4s subshell. So iron, as weird as it's going to be, iron will just have 2 electrons in the valence orbital. And then to form iron 2+, we'll just lose those 2 and we'll have Fe2+. For chloride, we drew this before. We'll have Cl with, we know there's going to be 8 electrons in 4 pairs there. So this is going to be the structure for Fe2Cl. Alright, so this brings us to the end of drawing Lewis structures for atoms and ions. Just to reiterate, a Lewis structure is simply just the symbol for the element with a number of dots representing the valence electrons. Now those dots could either be paired up or unpaired, and they represent the layout of the electrons in those valence orbitals. If electrons are paired up, then we represent them as paired dots. If they're unpaired, then we represent them as unpaired dots. For ions, we just draw the Lewis structures for the elements and then remove the dots as necessary for forming positive ions, or add dots as necessary when forming negative ions. In our next video, we're going to talk about how we can use this idea of Lewis structures for molecular compounds. So we're starting to build compounds now. We'll see you then. Bye.